All right, here we have the notes for section 7.4, sections of inequalities in two variables. So the graph of an inequality, so it says an ordered pair, A, B, of any real numbers is a solution of an inequality in x and y if the substitution x equals A and y equals B satisfies the inequality. The graph of an inequality in x and y consists of all pairs x, y that are solutions to the inequality. The graph of an inequality involving two variables typically is a region of the coordinate plane. So here's how, so what that means is, so just like an ordered pair is a solution to an equation if it gives you a true statement. So if I have, y equals 2x plus 1, the coordinate 2 comma 5 is a solution because if x is 2, y is 5 gives me a true statement. The same thing is true if I had an equation that looks like this. This point will say 5 comma 7. Oops, bad example. 12, yeah, that'll work. 12 comma 5 is a solution to this inequality because, no, it's not. 5, 12 is. Had it backwards. If x is 5, I get the statement 12 is greater than 11, which is a true statement. If you graph this, what we're going to have is a region of the coordinate plane. So here's your steps for graphing, or for drawing the graph. Draw the graph of the equation obtained by replacing the inequality sign by an equal sign. However, use a dashed line if you have a less than or greater than sign. Use a solid line if it's a less than or equal to or a greater than equal to. And then you're going to check a point in each of the two regions of the plane determined by the graph of the equation. If the point satisfies the inequality, shade the region containing the point. Now, typically, there'll only be one side that is true, so once you find the true side, you know what the false side is and vice versa. All right, so graph this inequality. So first, we're just going to pretend it's a line. Since this has the or equals to bar, we need to use a solid line to do it. So this is going to cross at 3, the slope is 2. So these would be my coordinates. And we do a solid line, looks like this. Oops. There we go. Mostly correct. All right, now, the second part is we need to, check a point. The easiest point to check is 0, 0, unless your line goes through 0, 0. So since the line does not pass through the origin, I'm going to check the point 0, comma 0 to see if I get a true statement or a false statement. So if I plug 0 into my equation, I get this, which becomes 0 is greater than or equal to 3. This statement is false. 0 is not more than 3, which means I cannot shade this side because this side is the false side. I would shade the other side. So any point from this shaded region would satisfy the equation. So for example, that point there is -3 comma +3. If I check that point, 3 greater than or equal to 2 times -3 plus 3, 3 greater than or equal to -6 plus 3, 3 is greater than or equal to -3. This statement is true, and that's true from any point I pull from over here. So if I do the point -4 comma 0, I should get a true statement. 0 greater than or equal to 2 times -4 plus 3. 0 is greater than or equal to -8 plus 3. 0 greater than or equal to -5. Also true. So any point from the shaded area will make my inequality true. Any point over here will make it false. If I choose the point 10, 0, this becomes 0 is greater than or equal to 23, which is a false statement. 0 is not more than 23. Okay, so the graph of a linear inequality determines a half plane. This is a plane. So if you draw a line through it, you cut it into two halves. Now, remember the coordinate axis goes on forever, so even though your line may be up here, it is still technically a half plane because there's a bunch of graph off to the upper left that we didn't see. The line itself is the boundary. So draw the graph of the inequality, state the boundary. So this, we're going to pretend it's an equation. So that's a vertical line through 2. It's going to be solid because I have the or equal to bar underneath. So there's my boundary. Now to shade, I need to choose a point from one side. If I get a true statement, I shade that side. If I get a false statement, I shade the other side. Now, x-only equations and y-only equations, the next part of this example, are actually relatively straightforward. You don't actually have to do math, you just have to think about what it's saying. This is saying x has to be more than 2. Well, if I look at my number line, the x's that are more than 2 are over here. So this side of the graph is where I would shade, where x is more than 2. So for this one, y less than -3, so I'm going to graph the line y equals 3, or sorry, -3. So that's down here. Now this will be a dashed line because I do not have the or equal to bar. Y is less than -3, so if I look at my y-axis, the side that has the y is less than -3 are down here. So any point from down here would work. Okay, example 3. Draw the graph of y greater than or equal to x squared minus 3. So we're going to graph y equals x squared minus 3 first. So you can do this in the t-table. So I actually know what the graph is. It's a parabola with its vertex at -3. So it's going to look like this, over 2 up 4, over 3 up 9 would be at 6. And it's going to be a solid line because I have the or equal to bar. So it looks like this. All right, so then I need to choose a point. 0, 0 is the easiest one to use, and my graph does not go through it. So I'm going to check my point 0, 0. So 0 is greater than or equal to 0 squared minus 3. 0 is greater than or equal to 0 minus 3. 0 is greater than or equal to -3. This statement is true, which means I shade the side of the line that has 0, 0, which is the inside of the parabola. Okay, you can also have systems of inequalities, where you have multiple inequalities and you're graphing them together. The solution of a system of inequalities in x and y is an ordered pair x, y that satisfies each inequality in the system, so it has to be work for both. So just like a system of equations, the x, y pair has to satisfy both equations. The same thing's true if it's inequalities. When we've found all the common solutions, we have solved the system. But it works the same way. So we're going to graph both equations separately. The solution area is where the shaded areas overlap. So for example, I need to graph y equals x squared with a dashed line, because it does not have an or equal to bar. I need to graph this with a dashed line. Now I'm going to rearrange this to make it a little bit easier to see, because it is a line. So y less than equal to just less than -2/3 plus 4/3 x. All right, so y equals x squared is a parabola. So it looks like this. And you could do a t-table to find this. It's going to be a dashed line, however, because it does not have the or equal to bar. Okay, so if I need to shade this one, I cannot use 0, 0 because my graph goes through 0, 0. I need to choose some other point that doesn't lie on the line. So I'm going to use this point here, 0, 4. So in this equation, I'm going to check 0, 4. So 4 is greater than or equal to 0 squared. 4 is greater than 0. This is a true statement, so I need to shade inside the parabola. I'm going to do the same thing. I'm going to graph this line. So positive 4/3 is 1 1/3. So it's going to cross the axis there. From there, it's going to go down 2 and right 3. So 1, 2, 1, 2, 3 would be right there. 1, 2, 1, 2, 3. Right there. So, and this will also be dashed. Let's go backwards. 1, 2, 1, 2, 3, 1. It's supposed to be here. So there's my dashed line there. And I need to check a point for this one. So I'm also going to check 0, 0 because my line does not go through it. So 0 less than -2/3 times 0 plus 4/3. 0 less than 4/3. This statement is true. So for the line, I have to shade the side that has 0, 0, which is below. So everything down here. And if you can tell, it's a little hard to see, this little section in here is where the shades overlap. So any point from that region would be the solution to the system. Okay. Alrighty, so you can do this with as many equations as you want. So this one will solve them all for y to get the line. So this would become y less than or equal to -2x plus 10. This one would become 3y less than or equal to -2x plus 14, which would become y less than or equal to -2/3 x plus 14/3. And these two are good to go. Now these two are just actually the axes, 0 and 0. So I'm actually only going to worry about stuff up here. It's going to save me a little bit of shading. They'll all be solid lines because they all have the or equal to bar. So this first one is going to cross at +10 and have a slope of -2. So it's going to look like that. Be a solid line. Okay. This one, 14/3 is 4 2/3, so about here. Slope of -2/3, so down 1, 2 over 1, 2, 3, down 2, 1, 2, 3, down 2, 1, 2, 3. We go backwards, up 2, 1, 2, 3. There. Also a solid line. Okay. So let's check our shading. Now I'm going to do a little bit of a shortcut here. Since x is more than 0, it has to be on the right side of the graph. Since y is more than 0, it has to be in the top half of the graph. So I'm not going to shade regarding these, but it's going to have to be up here. So I'm going to worry about the shading here. Now, neither of these lines go through 0, 0, so I can do 0, 0 in both of my equations. So there's 0, 0 in the first one. Here is 0, 0 in the second one. So 0 less than equal 10, well, that's true. So I'd have to shade below this line. So that's everything down here. 0 less than equal 14, that's also true. So I'd have to shade below my less steep line. So that this four-sided figure in the center here is the solution set. Any point in there satisfies all four equations. So for example, 1, 1 lies in there. If I plug 1, 1 into all of these equations, they all come out to be true. 2 plus 1 is less than 10. 2 plus 3 is less than 14. 1 is more than 0. 1 is more than 0. 2 comma 2 is also in that region. 4 plus 2 is less than 10. 4 plus 6 is less than 14. 2 is more than 0. 2 is more than 0. So those points all satisfy all four equations at the same time. Okay, so for linear programming, sometimes decision-making in management science requires finding a minimum or maximum of a linear function given by f equals something. It's called an objective function over a set of points. Such a problem is a linear programming problem. In 2 dimensions, the objective function f takes the form f equals ax plus by, and the set of points specified via a system of inequalities called the constraints. So like up above, these would be my constraints. The solution of the system of inequalities is a set of feasible points, so the shaded area, for the optimization problem. The set of feasible points is the feasible region, blah, blah. If a linear programming problem has a solution, it occurs at one of the vertices or the corner points. So your objective function, f of ax plus by, you would check the corners of your shape. So I would check 0, 0, I would check 5, 0, I would check, 0, 5, 5, 0, and that's at 4, comma 2. And see which of those give me the thing I want. Do I want to maximize? Do I want to minimize? Okay, so example 6 here says, find the maximum and minimum values of the objective function 5x plus 8y subject to the constraints. So this was actually the same region we had before, I believe. 2x plus y, 2x plus 3y. Okay, so I'm going to cheat. I'm just going to pull the vertices off of this. So the 4 vertices occur at 0, 0 had a corner. There was a corner at 0, comma 5. Actually not. It was 0, comma 14 thirds. 5, comma 0. And at over 4 up 2. So those are my vertices. So I'm going to plug those into my objective function. So the first one would be 5 times 0 plus 8 times 0, which is just 0. This one would be 5 times 0 plus 8 times 14 thirds. This would be 5 times 5 plus 8 times 0, which is just going to be 25. 5 times 4 plus 8 times 2, that's 20 plus that, so that's 16. And this one's going to be whatever 8 times 14 thirds is, which I don't know off the top of my head. It's 37.3 repeating. So this point here is the maximum. It's the largest of the 4 values. This point here is the minimum, the smallest. Okay, example 7. Produce is producing fertilizer with 2 nutrients, nitrogen and phosphorus. So nitrogen is going to be X, phosphorus is going to be Y. It needs at least 180 units of N and 90 units of P. So nitrogen must be greater than or equal to 180. P must be greater than or equal to, should use my variables, X, Y, greater than or equal to 90. Supplier sells 2 brands of fertilizer. A costs $10 a bag and has 4 units of N and 1 unit of P. Brand B costs $5 a bag and has 1 unit of each. Can pay at most $80 for the fertilizer. How many bags of each brand should be purchased to minimize cost? Whoops, those are not the equations I need. So X is going to be brand A, Y is going to be brand B. So brand A costs $10, brand B costs $5, and I have to spend at most $800. So for nitrogen, now let's see here. Brand A has 4 units, so 4A, and brand B has 1 unit of each, so plus 1B. So this has to be greater than or equal to 180. 1A plus 1B has to be greater than or equal to 90. So this is my system of equations. Now the other thing is I can't buy negative things, so I can actually set my origin down here in the bottom right-hand corner or bottom left-hand corner. So these are my axes. Okay, so what do I want to count by? Can I count by 10s? No, I have to count by 20s. Oops, that's 1. B. So this will become 10x plus 5y less than or equal to 800, 4x plus y greater than or equal to 180. This will become x plus y greater than or equal to 90. So I need to solve these for y to make it a little bit easier to work with. So this one would be y less than or equal to negative 2x and 800 divided by 5, 160. This one would become y greater than or equal to negative 4x plus 180. This would be y greater than or equal to negative x plus 90. So let's count by 20s. So this first one's going to cross at 160, so that's up. Actually, I can count by 10s because this graph is 20 by 20. So this one would be up at 16. So that's 15. So there's 16, slope of negative 2. So down to right 1, down to right 1, so on and so forth. Okay, so there's that. If I check 0, 0, I can tell we're going to have to shade. So 0 is less than 160 is true, so I'm going to shade inside this guy. This one, negative 4x plus 180, so that's going to cross at 18, which is going to be here, but slope is negative 4. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. 1, 2, 3, 4. So we've got that line. And it's going to shade 0, 0 is false. All right, let's do the last one first. 90. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9. The slope is negative 1. So I need that. Okay, so 0, 0 is false for both of these, so I'd have to shade above. So the solution set is actually this triangle-y shape here. So I've got one corner there, I've got one corner there, and I've got one corner there. Let's see here. Oh, I did graph an equation, didn't need a graph. To minimize the cost. So the cost function, no, that's right. So the cost function is equal to 10x plus 5y. So I check my corners. So 10, 20, 30, 40, 50, 60, 70, comma 20. 10, 20, 30. 1, 2, 3, 4, 5, 6. So 30 comma 60. And this one is over 10 and up. That was 16, so that'd be 14. Oh, no, 140. So I check those points and see which one gives me the smallest value. So 10 times 70 plus 5 times 20. So this will cost 10 times 30 plus 5 times 60. I think I'll be, no, so this one is, this one will cost me $600. And 10 times 10 plus 5 times 140. This one cost me $800. So that is the best bet. 30 bags of A, 60 bags of B, which is actually that point there. Alrighty, let's see what we got next. All right, so example 8, which I believe is the last one, yeah? Yep. Okay, Vela Manufacturing has 2 factories that produce 3 grades of paper, low, medium, high. Then you supply 24 grades of low, 6 of medium, and 30 tons of high grade. A produces 8 of 8, 1, and 2. It costs $2,000 per day to operate. B costs $4,000 to operate. How many days should each factory in order to fill at minimum cost? So my cost function is going to be given by 2,000 for factory A plus 4,000 for factory B. Let's see. I need to produce, so low grade has to be 24, medium grade is 6, 30 is high. Oops, that's low. So for factory A, let's see here, 8 ton of low, 1 of medium, and 2 of high. So 8x, 1x, 2x. It costs $2,000 to operate. Factory B produces 2 tons of low, 1 ton of medium, and 8 tons of high. So here's my equations. There's my restraint. So granted, once again, the origin can go down to the bottom left because I can't produce negative items or run factories for negative time. So this one would become let's see, move on. So it'll be negative 4x plus 12. So there's the low. This one would be y equals negative x plus 6. This would be y equals negative 1/4 x plus whatever 30 divided by 8 is, 15/4. So I would graph those equations, find the corners. Now, these are technically, the way I have it written, I need to produce at least these amounts, so look like that. So opens towards the y. So look like this. Okay, so if we graph, we get probably a really goofy shape here. So, yeah. All right, so this one's going to cross at 12. So 10, 11, 12 would be here. Slope of negative 4. Down 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. So there's my first line. This one's going to cross at 6, which is 1, 2, 3, 4, 5, 6 right here. Slope of negative 1. So it looks like that. 15/4 with a slope of negative 1/4. So 15 divided by 4 is 3 1/4, 3 3/4, 1, 2, 3 3/4. So down 1 over 1, 2, 3, 4, down 1, 1, 1, 2, 3, 4, down 1, 2, 3, 4. So, okay. So it's kind of hard to see, but the intersection points are 1 there. There should be 1 here. So that is at 0, 12. There's 1 at 2, 4. There's 1 here at 3, 3. And there's 1 way over here at, if I counted correctly, 15, 0. So I would just check those in my equation. So the first one's going to be, I'm going to actually work in thousands. So 2 times 0 plus 4 times 12. So this will cost us $48,000 to run. 2 times 2 plus 4 times 4. This will be $20,000 to run. 2 times 3 plus 4 times 3. This will cost us $18,000 to run. 2 times 15 plus 4 times 0. This will cost us $30,000 to run. So this is the best bet. Rerun each factory 3 days. Should be the lowest value. So 3 days each. These X and Y are both 3. And that is the end of the section.